Okay, I think I've got all set up finally. Welcome back, everyone. So we're just about to finish up our last topics in section 10.4. After that, we'll return to these notes right here. I said return to. We'll visit those notes there for the very first time and start reviewing for our upcoming third exam. Our third exam is kind of unusual. It's involving just 3 sections. That's because we're getting to some of the longer, a little bit more complicated topics. So I felt like not involving chapter 10 is probably a good idea for us. Also, because we're not really done with chapter 10. 10.5 is the section where we put everything together, and we're just not quite there yet. So the third exam will involve 6.5. And 6.5, we have to be familiar with using normal CDF and inverse norm in our TI-84 calculators. If you're happy with using those functions, then you're in great shape in section 6.5. Then when we get to section 8.2, that one's weird. I put it on the list because topics there are important and we do use them in section 9.3. There's no great questions that I could ask directly from that section. In fact, we said that is the most theoretical section in the entire course. Our whole goal there is just to look at pictures and see what the central limit theorem was just trying to say in that section. So there's no direct questions I'm asking out of there, and you'll see that reflected in the review questions up here. But all the concepts from 8.2 do appear over here in section 9.3. And section 9.3, as for the purposes of the calculator, well, there's really not a lot. What I would do for this is be sure to include the z-score table from section 9.3 and include it in your notes is what that's referring to. That's going to tell us the right critical number you would have to target for, say, 90% confidence, 95% confidence, or 99% confidence. And what I won't do on this exam is throw something like 92% confidence, since we only did that problem once, finding the critical number for one of those wonky confidence levels. So if you have that ready to go, then really there's no major special technique in section 9.3 for the confidence interval in the calculator. It was just grabbing those z-scores. So that's pretty much the extent of the TI-84. A lot of other stuff is going to happen in these sections. We have to give practical interpretations, know how to put the probability functions together. And same for section 9.3. We need to be familiar with all the confidence interval formulas and those kinds of things, as well as the interpretations. But we'll go over those when we are in our review section right here. So in a certain sense, this one is not as calculator intensive. I think exam 2 was a lot worse because there we were doing things like least squares regression, which is definitely tricky. Well, any questions at all, folks, before we get started? Okay, well, let's go and finish off our section 10.4. We'll be just a skip away from 10.5 being completed, but we'll pause, consider exam 3, and return to these topics on Tuesday next week. So here's not quite where we left off, but here's a good place for us to start. Essentially, the only thing that was new in section 10.4 is this right here. It's the z-score, or another way to say it is it's the test statistic, but it's not necessarily new. It's the same z-score formula we used way back in chapter 3. So with this right here, we're counting the number of standard deviations that your statistic p hat is away from the hypothesized value p naught in the null hypothesis. Standard error is not the same formula. It just looks the same. It takes the same form. But the massive thing that we have to be really, really careful of is observe how that goes inside here. But in chapter 9.3, the standard error formula for p hat, we don't have a null hypothesis. We are not assuming anything is true about the data. We're just looking at it and taking it exactly as it is. So we calculate the standard error here by putting p hat, 1 minus p hat, divide by the sample size n. And that's pretty confusing because this is the topic on the upcoming exam. This is the topic that would be on the final exam. But you wouldn't have a p naught value, so there might not be as huge of a danger of the confusion. Any questions so far, folks, about that standard error? Okay, then when we went through the problem, our goal is to calculate p-values. We already did that in section 9.3. And just as a reminder, if your p-value is less than alpha, the level of significance that has to be specified somehow or else we specify it ourselves. If it's lower, we reject the null hypothesis, and we say we have found evidence that the alternative, HA, is true. If your p-value is large, then that just says it's typical that p hat is close to p naught. It wasn't very far away at all. And we failed to reject the null hypothesis in that case. So that's information we've kind of talked about since section 10.1 in some sense, all the way to section 10.4. But hypothesis testing is confusing enough. It's always good to repeat these things on every single section. Then we went through this example here. This was set up from section 10.1, these hypotheses, just recopied. We calculate our test statistic from the data by taking the 0.34 and plugging it in right here for the standard error. Assuming the null hypothesis is true, allows us to calculate what is now the standard deviation exactly. Under that assumption, it's really true. We found that the statistic p hat at 0.33 was almost 2 standard deviations away from the hypothesized value of 0.34. That is pretty far. And so now we calculate a p-value of 0.0272 from this figure right exactly here. What we did was we grabbed our z-score, negative 1.9321, placed it here. We shaded to the left only because of the direction right here. If it's a left tail test, we shade the left tail. So that's the only reason we call it a left tail test. So that information goes into the calculator producing the 0.0272. Finally, part C asks us the question, will we reject the null hypothesis or will we fail to reject the null hypothesis? Those are the only 2 conclusions we can give on this study. Any volunteers for what the conclusion should be with that p-value? Honestly, it's kind of tough because we're not looking at the right information, right? I'm not sure if that's a small p-value or a large p-value, because what we need is that, the significance level alpha. Once that's on the paper, we can come back here. If our p-value is less than alpha, then we simply reject the null hypothesis in favor of the alternative. So always, if you're looking at the p-value, it's never the full story. It has to be compared against the level of evidence that we're after, 0.05. So let's say right here, since p-value, which is equal to 0.0272, then hold that thought, come here, compare it against 0.05, our p-value is smaller, so let's use the less than sign. It's less than 0.05, which is equal to alpha, and only because of the less than right there, we'll say we will reject H naught, the null hypothesis, in favor of HA, our alternative hypothesis. So that means this study found evidence the alternative hypothesis is actually true. All we have to do now is write that out as our overall conclusion to this problem. So now we need another practical interpretation. Any questions at all making this decision here in part C? Okay, so the part C decision is reject the null hypothesis. That means, let's just do it here visually, that thing is out of the question. We found evidence of this right down below here. All we have to now do is say exactly what that would mean. And it's really not too bad. Let's zoom in here a little bit more. Let me try to hide that window. There it goes. It's a lot of writing, like we mentioned before, but it's not too bad. We can say, to start out, there is significant statistical evidence that, then we switch gears and start talking about the actual parameter itself. So where the red dot is where I would be looking up next. We find P, go look up what it was stated to be. In most problems, we write it out ourselves, but this problem is a do-over from section 10.1, and that's why it's been just replicated right here. So we'll say there's significant statistical evidence that, I'll say the percentage, of all students that had not been absent at least once in the previous month. Jesus, a lot of writing. In the year 2000. So then we pause right there. We just said P, but we have to say what it means or represents using the context. Then right here, we'll just say literally is less than. Then change gears again. Now we're right over here. And because I said percentage in the problem, I'll say 34%. If you said proportion here, just as fine. Give it as a 0.34 and then it'll be more consistent. I'm not too worried about that. If you said proportion and gave me a percentage, I wouldn't take off a point. It would just read kind of funny. So I'll put here 34%. Coming from that value right over here. Then finally, that's the very full statement to this whole process. And that means we actually did it, folks. That's a real hypothesis test procedure from start all the way down to finish, giving the practical conclusion down here. Any questions or comments, folks, with that conclusion here? I might have. Let me take a look at this. It went A, B, C, D, or sorry, I guess I thought you were talking about the lettering right here.
Oh, so I'm is the answer for C if you just wrote out instead, or I just missed the B.
Oh yeah, we went to part D right after. Yeah. So what we said here is we're going to reject in part C. So we just sort of X that out. And when we support the alternative or say in favor of the alternative, all we really had to do in part D is just, oh, hang on. I see what you're saying.
Yeah, you have to get levels at 0.01 instead.
Yeah, I missed this part. Thanks for spotting that. You're on the right track. I'm missing that this is a whole new question. Sorry about that. So let me see if I can kind of just sort of wiggle my way out of this. Let's cut that, paste it down below here. And yeah, this should have gone together with the statement in part C. I missed this part. Somehow I just thought it was the next question for some weird reason. So we have our practical interpretation right down below. We'll leave it in that format. Thanks again for spotting that. That would have been weird to leave the notes just like that. Other questions or comments so far? Okay, now that we're done with part C officially, let's take a look at what part D is asking. Part D is saying, if we had alpha set to a 0.01, so we changed our level of significance in the study, this is a purely hypothetical question then. If this was a real governmental study and they received money from the federal government to do the study, and they probably did, this is a national study on students in the nation, then the moment they specified a significance level alpha, they would have done that before they collect a single piece of data. They can never change it again. And the moment they do something like that, that's considered massively unethical. They could not only lose funding, they could have more serious consequences happen to them. So think of this as purely hypothetical. What if it was at a 0.01 is what we're saying. So let's change this, regard it as a 0.01. We need to look at our p-value again. It's at 0.0272, still hasn't changed. But now when we compare, we can say this time, let me start off the same way. Let's say since the p-value, which is equal to 0.0272, let's do an immediate comparison, 0.0272 compared to the 0.01, it's now bigger in that second decimal place. So this is bigger than 0.01, which is equal to alpha. Now, this time, purely because of the greater than sign right here, the decision will be, we will fail to reject H naught. So we did not find evidence that the alternative hypothesis is true. We have to just, well, maybe Xing it out is a little bit severe, but we didn't support the null hypothesis either in this problem. So one thing we cannot say in this question in part D is we found evidence that the proportion of those students is 0.34. We have no idea until they take an official census and actually measure everyone, how many times they were absent the previous month. So here, this conclusion is definitely a little bit weird, but it's important to make this kind of conclusion. We would say here, with lots of sadness, people really want to support the alternative hypothesis. That's the reason the study started. But if they can't do it, this is still important information to say there is not enough evidence in the sample data to conclude. And then we start this all over again. You might say ditto or something like that, but let's write it out in full. We didn't find evidence to conclude that that's true. We still have to write out all that information. So to conclude that, the proportion of all students that had not been absent at least once. I really should have picked a smaller statement for this thing, but we're almost there. At least once in the last month in year 2000. Now, change gears, we'll say is less than that 0.34%. Let me go to that light blue color. I said 0.34%. That's weird. I went for the proportion. So this is 0.34 as a proportion, not as percent. Sorry about that. So we got it, folks. Really, the only thing that happened to this one is we had to admit that there is not enough evidence, or we failed to show that this is true right down below here. What did I click on this time? What in the world? We'll just ignore that. So again, the only conclusions is that we found enough evidence that the alternative is true, or we failed to do so in these kinds of studies. Any questions at all, folks, on either one of those conclusions? Okay, well, that's the conclusion of these entire notes. Okay, want to get rid of too much of that. But one thing I did want to mention before we go to the review is hypothesis testing is weird for a lot of reasons. Imagine you yourself are in charge of this national study. You're reporting to the federal government, possibly in front of a Senate committee, something scary like that, to present your findings. If this was a federal agency-sponsored study, that would probably happen. Then let's suppose we're in this situation. We did have alpha set to 0.05. We really did reject the null hypothesis. And you read out to everyone in Congress or in the Senate, this statement here. It would be totally correct and people would be happy with this, but then they're going to want more. Anyone see what you would probably want to know more about this once you make that conclusion? It's kind of almost a weird question, but imagine saying this. You told everyone in the Senate committee, we have found significant statistical evidence that the proportion of students who had not been absent at least once is less than 34%. People might say, gosh, that's bad, but they're going to immediately all ask you this question.
Why?
Absolutely, they're going to want to know the reasons that might be contributing to these problems, but they're also probably going to want to know, well, what is the estimate for this percentage currently? In other words, if it's less than 34%, okay, great, but by how much? Is it 10%, 5%, 2%? Would have to answer that question as well. So we want to think of the hypothesis test as the overall test. We found that there is a difference, that something is really less than 34%. But after doing a hypothesis test and getting a conclusion where you reject the null hypothesis, we would want to do a follow-up test. The follow-up test, or test is the wrong word, the follow-up procedure, the follow-up procedure would be a confidence interval for P. Unfortunately, we can't ask those kinds of questions in class because then the problem becomes just majorly really, really long. But it's important to know that hypothesis testing and confidence interval procedures, they don't exist in isolation. They go hand in hand. And for these kinds of conclusions, if you did a hypothesis test, you are almost certainly doing a confidence interval afterwards to estimate the value of P after the fact. So if it's less than 34%, we want to know by how much and see what the full confidence interval estimate would even be. Even if we were here, if we failed to reject the null hypothesis, it still might have been a good idea to do a confidence interval anyway, to just see what the plausible values for that proportion would have been. Well, that's the last comment I wanted to add on these notes before we turn to the review next. Any questions or comments, folks, before we change gears? Okay, so that's hypothesis testing so far. Let's save these notes, and now we're going back to normal distributions and confidence interval procedures. So we are going back to reviewing on these notes right here, sample exam 3, version 2, and it's a Word document. Let me try again. Okay, here's the actual Moodle page. So we're going to these exam 3 review problems here. What I did is just put down 4 really fast problems for us to take a look at when we open the Word file for them. If we run out of questions here, we'll probably spill over to this document, sample exam 3. So here's how it starts, just 4 kind of random questions altogether. Problem number 1 just starts off by saying, Rochester, New York averages 21.9 inches of snow for the month of December, which even for people in Idaho Falls, that's pretty brutal. The distribution of snowfall amounts is normal. So we have a normal distribution with the standard deviation of 6.5 inches. In our context, we're going to let a variable x represent the amount of snowfall in Rochester in December of this year. So think of it as 2023. Next thing I would do before even launching too far into this problem is, let's start recording what the population characteristic values ought to be. When it says averages, we have the value mu equals 21.9 inches. We're not saying we know that mu is exactly 21.9 inches. That's just going to be our best guess for that population characteristic. Next, there's a standard deviation of 6.5 inches. We'll use the value sigma because it's describing a population at 6.5 inches. So now we're dealing with purely numerical data on these problems here. It's been a while. Part A is asking us, what is the probability that Rochester will experience 10 inches of snowfall or less this year? So they have a really, really light snowfall year, and we'll round to 4 decimal places. So I didn't say it on this problem, but I think on the official exam, what I would be writing on every one of these is include a graph. Let's put it in here just to be specific this one time. The reason for including a graph is these questions are not easy to score on a partial credit basis. In the calculator, either you have the right number or you don't. And so the way that I do try to award partial credit is through the organization. And the organization of this problem is essentially entirely inside the graph. So it'd be something like this, a really fast normal curve. Doesn't have to be too fancy. Putting in the center of 21.9 is definitely a good call. And I usually get in this habit of just putting both the values to the right just so that they're visible. You don't have to do that. Next, let's go back to the question itself and reread what they were asking. What is the probability, so let's write probability of something, that Rochester will experience 10 inches of snowfall? X is the snowfall amount, so we can say X, 10 inches with a little bit of space, or less. So we're wanting X to be less than or equal to 10 in this problem. All we have to now do is, well, let's put our value of X somewhere on this. At 21.9 inches, 10 inches is pretty far to the left over here. I'll just throw it down here. I wouldn't want to think too much on this part of the process. We're just organizing the information. So here is the 10 inches from the problem. Shading to the left kind of helps us to decide what the next input would be. We'll go for input 1, negative 10 power 99. Input number 2 in your calculator is this value 10. Mu and sigma are always the last two, but I'll still get in the habit of putting them there just so it's apparent. Then back in the calculator, let's see what we get out of this. And by the way, if we did miss this question, let's say it's a 4-point question or something like that. I haven't decided officially on the points. But if it was a 4-point question, and I totally miss it right here, my answer is not right in probability, but the graph is accurate, I would give half the credit on this problem. So you get half credit for just as organizing what should go in the calculator. Now back here, hit second and barbs to pull up your distributions. And there's already a kind of a conundrum. We will either use normal CDF or inverse norm. Any volunteers for which one will give us the area? Exactly, we want normal CDF to pick up area. So hit enter here. And if we guess wrong on the function, if we're not sure or we're nervous, it'll help out because it's asking for 4 things, a lower to upper value. You'll know you're in the right place. So negative 10 power 99, it's already set. Positive 10 goes in here. Then 21.9 and a 6.5. So in this calculator, I'm going to get a probability of 0.0336 upon rounding to 4 decimal places. And that's pretty much it. This is now saying if you're going to Rochester, I'm not sure if I'm saying that right, Rochester, something like that, New York, then there is about a 3% chance you'll have to shovel less than 10 inches of snow on your front step or something like that. So it's not very common. It's probably going to be way worse in that place in New York. Any questions at all, folks, on getting that value, 0.0336? Okay, if anyone has any trouble on their calculator, please let me know right away, either after class, through email, things like that. I'll be very happy to help out. Even over the weekend, if you're studying on this topics and something weird happens in the calculator, just take a quick picture of it, show me the error, and I'll do my best to try to reverse engineer and work through it to try to get it working. But let's try another one then while we're here. We want the probability that X is between 10 and 20. Then after we find that probability, for this one, we'll give a practical interpretation and we have to use the context for full credit. So usually a question like this one might have 2 additional points because there's extra work to interpret what we get. So we'll start off by putting down a nice, fast and simple graph to organize information. Okay, so that's the basic graph. From the probability statement here, let's put a value of 10 way over here, value of 20. Well, that's not too far. That would be around the center. And we want to find the probability that we are in this range. So now we want to know what's the chance that you'll have to deal with 10 up to 20 inches of snow in the month of December in that state or city in New York. So that's the area we're trying to find. just always seems like a good idea to just reduplicate the function. So it just trains our eyes to know where to look when we're getting the right value. So with that function there, I forgot to put the 10 and the 20, but we're pretty much ready to go. Input 1 is our 10, input 2 is the 20, and here's input 3, input 4 in the calculator. So another really fast computation. But any questions first, folks, on organizing this graph? Yeah.
So for the 20 that you have there, is that supposed to be on that side of the function?
Oh, good call. It's supposed to be right over here. Thanks for spotting that. For some reason, it just seemed right when I placed it down, but no, that absolutely ought to move. And ordinarily I say, it doesn't matter where it goes too much, but it does have to matter where it goes relative to center. That could really cause us some trouble when we go to look at our answer. So thanks so much for spotting that. Good eye. That one should move a good amount to about right here. So 20 in this location. So that's input 2. We'll just extend the arrow on that one. And that means our area, it looks a lot less this time. If I extended way over here, that's closer to 50%. Now it looks like maybe 30% or something like that. If I got something small in the calculator, but I drew it incorrectly, then the graph is doing more harm. I might think a correct answer is actually wrong. So thanks for spotting that. Other questions so far? Okay, let's go back here and throw everything back into the calculator. So second vars down to normal CDF again. We have a new lower of just 10 inches. The upper boundary is 20 inches. And the last two parameters are put in correctly still. So now this one comes out at 0.3515 altogether. So 0.3515. And when I put that 20 in the wrong place relative to the center, I was thinking, oh, that looks about close to 45 or maybe 50%. So now that it's correct, this does look like the right answer finally. Well, this one is not quite done. We still have to give an interpretation, but there is a pattern to these kinds of problems that you ought to expect to see on the exam as well. If a problem is indicated in this way, you're probably going to write down the probability function and the graph. But if the probability statement or function has been given, then you're almost certainly going to interpret your answer right after. So these problems kind of go in reverse to each other in that way. But this is honestly not too bad. It's pretty similar to what we've been doing all along. We'll just go over here, convert that to a percentage, and we'll start by saying there is a 35.15% chance that, now we go to X. X is between 10 and 20, but we have to bring in the context and say amount of snowfall in Rochester in December of this year. Let's actually highlight that. That seems like a good value to highlight here. So there's a 35.15% chance that the amount of snowfall in Rochester, I think I pronounced that like 5 different ways already today, in December this year, then we just go over here and here and say will be between 10 inches and 20 inches. So a significant chance of doing quite a lot of work in December. Well, any questions, folks, on the conclusion of this one here? Okay, now we go over to part C. Well, what I said before, with these functions, if the probability statement is given, then you're probably going to do a practical interpretation. Definitely happens on this one here. But this problem is bizarre in a certain sense. On everything we've been doing, we've been tasked with finding the probability. The moment they give us a probability like this, here's when we're going to use inverse norm. So only because of a given probability use I and V to stand for inverse and norm. And it's really a true inverse. If they give you an area, you can reverse engineer and get the X values. But if you get the X values, you can find area going backwards. It starts and finishes really the same kind of way, though. We begin by drawing a really simple graph to represent the situation. So here's center 21.9. I think the real reason I got in the habit of copying these down is just so that they're visible when we scroll through the page, they don't go away. But now over here, to solve probability, X less than K equals 0.25. One of the more critical things we ought to do is place K on the X-axis. So our value for K, one thing I did want to add to these graphs, which is totally optional, but sometimes it helps a little with the context, is I like to add X here. And X would be snowfall in inches. I just kind of forgot on that one. And also we're doing review problems, so we're trying to do as many of them before we run out of time. But that's a good thing to add to your graph because it will help with interpretations. We're just forced to think about snowfall when we write that in. Now, K being right here and the less than sign is saying the area to the left of K would be 25%. Let's write that in. Only because of the less than right here, we want area to the left of K to be 0.25. That means I couldn't put K over here. Area to the left of K in this location would be about 75% or so. Here, right at the center, it would be exactly 50% to the left. So K should be somewhere around this end. And again, as long as you have it somewhere around here, you're in great shape. It doesn't have to be placed perfectly. So I'll just kind of throw it here. Well, that looks kind of small. Maybe just a little bit more to the right. But definitely don't fuss too much about it. We'll know exactly where it should be once we calculate K and find its value. One thing that we should add, though, is what goes here is going to be 0.25 in area. So I'll shade this kind of lightly. 0.25 goes here. And a strong wording with our calculators is that for most people's calculators, the TI-84 only will deal with area to the left. So if this was a greater than sign, and I had an area right here, I would have gone 1 minus 0.25 to get the value that goes in that location. But here, we're actually pretty much set up to put everything into the calculator. First thing we put in is input 1 here for area. Then the same last two inputs, the mean and standard deviation. So let's throw this in, but any questions first before we go to get a computation on this one? Okay, so back to the calculator. It's actually doing quite a lot when it does this. We go second and bars to start out. Look up the inverse norm, just right under normal CDF, option 3. You'll know you're in the right function because it's asking for the area, which is the only thing the problem essentially gave us in a certain sense. So 0.25 to start, then 21.9 for mean, and 6.5 for the standard deviation. This is kind of tricky because we sometimes get used to mu and sigma being auto-filled in when we did it once up here for the first question. But if you switch the functions, you have to put in the new values here. So definitely double check everything's right. Then after enter, here's what we get. It should be about 17.51 inches, rounding to 2 decimal places on this one. So K equals 17.21 inches. Then definitely kill, or sorry, say again?
17.5.
72.51, thanks for mentioning that. 51 inches. Almost thought I had it hidden, but back over here, Also, definitely take a look at the graph. If it looks like it's not less than 21.9, kind of like the mistake that was over here, then we probably gave it the wrong area. Just reconvene, go back to the calculator, try again. You might have had a wrong value where you need to go 1 minus a 0.25 or something like that. Or maybe the direction was a little bit confusing and we're just shading in the wrong spot. But if you get in the habit of always placing K and then comparing it with the center, that is a great way to catch a lot of very, very simple mistakes. But now we have to go to this right here and give a practical interpretation. Any questions or comments first? Okay, well, it goes pretty much the same exact way. Here we could say there's a 25% chance. That. Now we're talking about X, so we can highlight that in blue, the amount of snowfall in Rochester in December will be, go back to our value for K that we just found. Also, we have a direction, so we'll say less than 17.51 inches. And that would be our interpretation for this problem here. You could also give a slightly different interpretation if it just feels like it makes more sense. Let's put this in brackets. You could say the 25% least severe winters in Rochester will have 17.51 inches of snowfall or less. There feels like there's a contradiction between these two statements, but also keep in mind, normal distributions are weird because probability X less than or equal to K is the same as probability X is strictly less than K. So in your interpretation, you could say less than 17.51 inches, or you could say equal to 17.51 inches or less, like we did in this interpretation below. That's a side comment, so let me kind of just put it in a box so it doesn't cause extra confusion. But any questions at all, folks, with our conclusion there? Okay, so in this problem, we know that 25% less severe winters, and then part D is asking, well, what is the 1% of worst cases for the month of December in Rochester, New York? Now, for people who like snow, this is not a great question on a real exam. Worst was intended to mean more snowfall. Some people might be happy about that, but we're thinking of that as being bad when we said it in this problem. If this was a real exam question, I would have to specify a little bit more. Well, if we're talking about the 1% worst, we at least don't have to give a practical interpretation to this one. It's given it to us. We just need to find what is that level of snowfall. So this whole problem is all about solving probability X. We compare it against K once again. Then this word causes more confusion than it was really worth, but it gives a directionality of greater than, meaning more snowfall. They want this to be at 1%, so we need to take that, convert it to a decimal, 0.01. Now that we have that, we can throw this information into a graph. We needed the probability statement to really know what goes where. So here's our graph once again. This one was kind of low effort, but it still looks like a normal distribution somewhat. So we have a mean here, next to sigma is at 6.5 inches. And last thing we have to do is place K. I forgot to put the X right here, but again, that's a good thing to throw in, but if we're short on time, say on a real exam, or like me, where I have about 5 more minutes, if you didn't put it in, that's okay. But it sometimes is definitely well worth it, especially if you know you're giving a practical interpretation. I'll put it just simply as X. Next, we have to place K, And if I placed it here, it wouldn't be quite right. And that red dot in that location, we are talking about the area to the right of K being a 0.01, but that would be more like 99% if we put it right there. So instead, we put our value way over here. So here's what, well, at 1%, you probably want to go a little bit further to the right. So here's K. It would be even further to the right there, but don't worry too much about trying to make a perfect graph. Just make it close to believable. So in here, we have an area of 0.01 in that location. So that area is absolutely no good to us this time, unless you have a calculator where you can specify a right tail. Some folks do have that in class. For most typical calculators, you will only accept area to the left, especially if your calculator looks a little bit more like this front plate here. So we need to find this area. And there is a trick to this. It's the complement rule. The total area under this curve is 1. The entire real number line is the sample space. So the probability of any real number, all the area under the curve should be exactly 1. And that means we can go 1 minus the 0.01 to get a value for the area here, which is 0.99. That would be the area that most calculators accept because it will be the area to the far left. So we're pretty much there. Here's input number 1. Use this area. Same inputs 2 and input 3. And so now we're about ready to get a value. Any questions or comments first, folks, with the organization here? Okay, let's go over to our trusty calculator. Back to second bars. Inverse norm again. And we'll put in area 0.99. Then mu 21.9, 6.5 for sigma. That looks about right. Hit enter through all these. And definitely don't celebrate early once you get a value. Be critical about it. See if it looks like it makes sense. Center is at 21.9 inches. So K being really far to the right, that does look believable. It should be around, that looks like a few standard deviations. Take 6.5 times 3. It's like you're adding 18 to 21.9. So let's take that, 37.02, and that's our value for K. Let me see if I got it this time, 37.02 inches. Somehow I conflate some of these digits sometimes. I think we got it. So this value right here describes the 1% worst time you'll have in Rochester, New York if you go there this winter. You could be around 40 inches of snow that you're shoveling. That sounds pretty horrendous. This problem doesn't need a practical interpretation because the question is the practical interpretation in a certain sense. Well, any questions or comments, folks, on this conclusion here? Okay, well, we did it. And if you can do these same kinds of things in the calculator, you're in great shape for the upcoming exam. On Thursday's class, we'll take a look at a confidence interval. We'll try to just do as many problems as we have after that. We'll decide if we want another 6.5 problem or another confidence interval problem is also down below. With whatever we do on Thursday, I will solve everything on this document. So the solutions will be fully posted right here in case you want to take another look at them for your studying on exam 3. Well, that's all I have for folks today. Any last questions or comments? Okay, have a great night, everyone. When we come back on Thursday, we'll just be back on this document.